Hey guys, I just wanted to look through another power series where we develop a power series from the geometric series. So this is number 17 from section 11.9 in your book. And you're supposed to write a power series for this function f of x. I got a question on this from a student, and the student had come up with an infinite series that works, but what they had wasn't a power series because they had they used like 1 over 1 plus 4x to make the power series, and then they multiply the whole thing by x over the other 1 plus 4x. So they got a valid series that's equal to this, but it's not technically a power series. Remember, a power series has to be a coefficient that's like a function of n, and then times x to the n power. So having the other x's in there, especially in the denominator, makes it technically not a power series. All right. So with this one, you do want to kind of relate it though to that basic form of a geometric series, 1 over 1 minus r, right? So what I am going to do is I'm going to leave that x off first, and if we do that, just focus on 1 over 1 plus x first, right? And sometimes it's helpful to do little changes one at a time. Say, okay, I'm going to start here with 1 over 1 plus x, and I want to end up here, x over 1 plus 4x quantity squared. So 1 over 1 plus x, that's like 1 over 1 minus negative x, and that turns into this alternating series, right? You're basically plugging negative x in for all the x's in that geometric series. Okay, got the general term here. And then the next step for me was, okay, I want that x to actually be a 4x. So 1 over 1 plus 4x. So to do that, I just plug 4x in where those x's are now, right? Or negative 4x, I guess. So 1 minus 4x plus, again, it's alternating series because it's plus in the bottom instead of minus. And these are just powers of 4, right? 4, 16, 64. So over here, 4 to the n. And you have x to the n. And it's alternating. And you always just, when you write that general term, you always want to double check, make sure that it matches that first term. This is x to the 0, right? Because it's 1. So this is n equals 0 term first. And if negative 1 to the 0, it's going to be positive, so that's right. Now, this is 1 over 1 plus 4x. We're almost there. I need an x on top. That's no big deal because you can multiply an extra x on later. But on the bottom, I need that 1 plus 4x to be squared. So I have to think, how do I get from here to having that squared? And that's where you can use some calculus. This is 1 plus 4x quantity to the negative 1 power. So if I take the derivative of that, I'll get negative that to the negative 2 power, just like this, and then times a 4 for the chain rule. So take the derivative with respect to x, and notice on the left side, 1 plus 4x to the negative 2, right, times negative 1 and times 4 from the chain rule. So this is what the left side of this will look like. And again, we're a little closer now. We got this extra negative 4 that we're going to have to get rid of, but we got the 1 plus 4x squared on the bottom, and that's important. And on the right side, all I did is take the derivative again of every term. So 1 goes to 0, negative 4x goes to 4, this goes to 32x, this goes to 192x squared. But again, sometimes it pays to kind of keep those factors separate, right? So if you have this one and this one, it's just easier to get that pattern, right? So what I really have is 2 times 4 squared, right? 1 times 4, 2 times 4 squared, 3 times 4 cubed, n times 4 to the n, or n plus 1 times 4 to the n plus 1. Your general term might look different than mine. You might have kept your index like the same, and I just kind of adjusted to make it so that this was still the n equals 0 term, right? With x to the n, right? And then 4 is to the n plus 1. Notice I have a 4 there, right? I had to make the alternator work, so I had to put a plus 1 on that one, and then the n plus 1 multiple there as well. This is the 0 term, so n plus 1 is 1 then, so that works. Okay, so we're almost there. The only thing I have to do now to get from here to here is I need to get rid of that negative 4, so divide by negative 4, and I need to multiply by x. So I'm going to multiply by negative 1/4 x on both sides of this equation. There it is, and that's what I get. So on the left side, I get exactly what I want, right? The negative 1/4 cancels out the negative 4, and I get the x on top. And on the right side, negative 1/4 x, that negative 4 goes away, becomes a 1 times that. You see how it works, right? And again, keep that pattern, and make your general term work. And you can change what n is at the beginning. If you're not sure, you can write n equals 0 or n equals 1 or whatever you got for that first term. You just want to make sure that it's internally consistent. And then that's another way to write this one, the series from 1 to infinity. And this way it makes it very clear where it starts at n equals 1. Okay? And here's another way to write that, kind of condensed a little more. I put the 4 to the n minus 1 together with the negative x to the n, and adjusted to make those powers the same by taking the 1/4 out. But that's that. And then you could do the ratio test to get the interval of convergence here. Because it's 4x to the n, or negative 4x to the n, that radius is going to end up being 1/4, right? Because you need the base in a geometric series to be magnitude less than 1, right? So when x is less than 1/4 in magnitude, this will be a base with a magnitude less than 1. It'll converge. When x equals negative 1/4 or positive 1/4, then you have a base. Even when you get the base of negative 1, because the rest of this is an n, it's not going to converge then either. So the endpoints won't converge here. Okay, so that's that. That's our power series. Notice that each term is an x to the n, right? You could look at it this way, x to the n, and then the rest of it is like this. Actually, it's better to look at here. The rest of it is this c sub n, right? So all of this is your coefficient in terms of n, and then times x to the n. That's how you know it's a valid power series. All right, hope that was helpful. Let me know if you guys need more. Thanks.